All right, what's going on, everybody? Today we're doing another LeetCode problem. This one's called binary tree right side view. So we're basically given a binary tree. They want us to imagine ourselves standing on the right side of the tree and then returning the values of all those nodes we can see. So basically, if in other words, if we were to do like a level order traversal of this tree, we'd want to return the rightmost node on each level. So we can see for this tree, obviously the result is going to be, all the rightmost nodes here. It's just we have this 1, this 3, and this 4. And those are the only nodes we want because at every level, basically every node preceding this 3, every node preceding this 4 is going to be obstructed from our view. So we just return this 1, 3, and the 4 from top to bottom in that order, just in an array of integers or a vector of integers they want. For C++. So let's go ahead and look at another bigger example. So I drew up another tree here, and we can see that the result for this example, for this tree, if we look at the rightmost node here at the top level, it's obviously going to be 1. For the next level, 3 and 7, and we can look at the rightmost node for every level and then see that this is the output we would want here. So we could do a level order traversal. I prefer to do a recursive depth first search whenever I can for these tree problems because they lend themselves very well to that. So let's go ahead and go for that approach. I'm going to erase this result and just pretend like we don't know what that is and we're stepping through this algorithm for the first time. So basically, we're going to be starting at this node, and the key metric here is at each level we're going to be passing in to our recursion the level we're at. So right now we're going to be at level 1 and for this node, and let's I'll actually write that here with this arrow. So, and we're just going to add 1 every time we go down the tree. And we're going to ask, since we're doing the way this is going to work, since we're doing a post order traversal, since we're passing in the rightmost node first always, we can just have a simple condition where we ask, okay, is the level of this node greater than the size of our result vector? And since we're passing in those rightmost nodes first, we know that when this is true, we need to add this node to the result vector. So I'll show what that looks like all the way down the algorithm. So we're going to add this 1. Okay, now we're going to do our post order traversal, our depth first search. We're going to pass in the rightmost value first. So we're going to have, again, increasing our level. So we're going to be at level 2 now. Is the level we're at greater than the size of our result array? Yes, so we need to add this 3 to our result. Okay, once again, depth first search on the rightmost node. We're now at level 3. Same thing. This is greater than the size of our result array, so we need to add that 7 to our result vector. Okay, we're at this point we would be passing in null nodes. So every time we see a null pointer, we're just going to return. So now we have to search left. We're still at level 3, right? Because 2 plus 1 is 3. That's not bigger than our result vector, so we don't have to do anything. We would try to go this way, it would be null. Then we would try to go left, and our level here is going to be 4. Is that bigger than our result vector? Yes, so we're going to add that 8. Okay, we're going to end up popping all the way back up now to our 1 and finally searching left. This is going to be a 2. Okay, is this bigger than our result vector? No, so we can keep our depth first search going, always right first when we can. So we see a 3 there, bigger than our result vector? No, so we pop back up and then we can search left. That's going to also be a 3 there. Not bigger than our result vector. We're going to go right. Now we have a 4, still not bigger than our result vector. We're going to go right again because we always go right first when we can. We have a 5. Okay, now this 5 is the level we're at now is finally bigger than our result vector. And again, since we're doing a post-order traversal, this 11 belongs in our result array. So we're going to add that 11 there. And then we pop back up to the 4. We go this way. The level here, 3 plus 1 is 4. And that's not bigger than our result vector. So at that point, we visited every single node and we've constructed this right side view like they requested. So in a nutshell, that's basically the algorithm. The time complexity is going to be big O of n because we obviously need to visit every node here like we just showed. So big O of n, where n is the total number of nodes in the tree for the time complexity. And then for the space complexity, we're going to have big O of h for our recursive call stack. Recursion does necessitate some extra memory, and that's going to scale with respect to the height of our tree. So big O of h space for the time complexity. Okay, so let's go ahead and get into the code. There's honestly not that much code for this problem. So we do need to implement a separate recursive function, but the first thing we can do is just initialize a vector a vector of integers called result, just for that resulting vector. And what we're going to do is I'll just call this depth for search. It is a post order traversal, so just something to keep in mind. So that's very important because they don't want the left side of the tree, they want the right side. So we could easily adjust this problem to return the left side of the tree, or easily adjust this algorithm. So we're going to call depth for search on a node, right? So first we're going to have the root node. We're also going to pass in the current level we're at. So with the root node, that'll be level 1. And then we also need to pass in that result vector just by reference. So, and then at the end of that, we'll return the result vector. So let's go ahead and implement this recursive DFS function. So we'll make it a private function member. It will return void, and it will be called DFS, of course, because that's what we called it. And then we're going to have a tree node for whatever node we're at. I'll just call that TN. We're also going to need an integer for the level we're at. And then we're going to need our result vector of integers by reference, because we're modifying that kind of globally within this function. Globally, quote unquote, I mean, it's going to live in this function, but we don't want to modify it. We don't want to have a separate result in each of these, recursive calls. It doesn't make sense. So by reference there. So the first thing we're going to do, right, is we need to check if we're at a null node for that base case. So if not tree node, we can just go ahead and simply return. Okay, so the next thing we want to do is we're going to use that metric we discussed, where we're going to have an if statement. We're going to check, okay, is the level we're at currently greater than the basically the size of our result vector, so res.size. And if it is, then we can go ahead and push back. We're going to do res.push back the value of the tree node we're at, so tn, the pointer to that value. Okay, and then we can proceed with our recursion. So basically we want to call the right child first, right? So we're going to call depth first search on the right child. We're going to pass in that level +1, incrementing that every time we go down to the child nodes, and then we're going to push in that, pass in that result as well. So that's pretty much it. We just need to do that with the left child also. And at that point, that's pretty much it for the code. So let's go ahead and run this. So yeah, all right, no bugs, so we're good to go there. So that's pretty much all for the code, and I already discussed the time and space complexity, so we should be good to go. So hopefully you gained some knowledge from this video. Hopefully it helped you understand the problem better. If it did, leave a like and subscribe, and I'll see you guys in the next piece.